looking at the worksheet with the graphs on there, f prime is greater than 0, so that means f is increasing. F of 0 equals 0. Again, that's usually our favorite information because it's the easiest, and you can go directly put it on the graph. As x approaches infinity, the limit equals 2. That's not worded right. Like, that should have an f of x in there, but I think most people figured out what it meant. So as x gets really big, the graph approaches 2. So that sounds like an asymptote thing. As x goes to negative infinity, the graph gets closer to negative 2. And we're always increasing, so something like that.
And then the 0, 0 would be a point.
And 0, 0 is a point. Yes.
No point.
Not necessarily. It wouldn't have to be. I mean, I drew it that way, but there's nowhere that tells me that 0, 0 is the point of inflection. We could... I could try to draw it where 0, 0 is not the point of inflection. But I think most people would just draw... It would be nice and symmetric if the origin was the point of inflection. But that wasn't required, so there's other ways to get there. All right, part F. Okay, there's a lot of information in graph F. It's not that it's really that hard. There's a lot of stuff going on. Let's see. I'm sort of scanning for the easy stuff first. F of 0 is 3. F of 3 is 0. Like that. F prime of 0 is 0, so that means there's a horizontal tangent line at 0. And the rest of this stuff is about increasing, decreasing concavity. So we're increasing. F is increasing when x is less than 0. F is decreasing between 0 and 3. So increasing, decreasing to 3, and then increasing after that. And again, you don't have to label the graph, but maybe it helps. Right, F is increasing when x is greater than 3. Yes. Okay, so I've got my increasing, decreasing on there. So increasing, decreasing, increasing. Now, thinking about concavity, x less than 3, we are concave down. F is concave down. Less than 3. So over here, concave down. Greater than 0, or yeah, x greater than 3, we're concave up. So, let's see. Increasing and concave down up to 3. And then, up to x equals 0. Then from 0 to 3, we're decreasing and concave down. I need to be careful. On the last one, we're increasing and concave up. So something like that for that graph. Checking with the key to make sure I got that right. A lot of pieces to that one. I think it's helpful to sort of label the graph as you find the information, but you wouldn't have to put this on there. But otherwise, your brain has to hold all that information. Question on that one? There's one or two like this on the test where we give you some stuff and ask you to graph it. I don't think any of them have that much information on there. But hey, if you can dodge a wrench, you can dodge that. So that was the wrench problem. All right, let's go through this one. And I saw that many of you had given it a try. So let's keep picking on people here. Whoops, can't pick on Sarah. She wasn't here yesterday. Actually, I could pick on her for this. Sorry, Sarah, put you on the spot here. Y-intercepts, because that's not a calculus thing. That's an algebra thing. Now, you weren't here for the reminders yesterday, so I will say to find x-intercepts, you set y equal to 0. So, Sarah, to find y-intercepts, we set x equal to 0. And if we plug in 0 for x, what do we get? What's that? 7. So, again, I think I mentioned this yesterday. Some people fill out the whole sheet and then put the stuff on the graph. I like to fill it out as we go. 1, 2, 3, 4, 5, 6, 7. Because then, as I fill in more and more points, it starts to make sense. And if you get something that looks out of place, it's probably because you made a mistake somewhere. So I think filling it out as you go is helpful. Asymptotes. Well, I guess somebody gets the easy one, right? Tierney, what asymptotes are there? Oh, I did it. I put somebody on the spot after saying it was an easy question. This is a polynomial. Polynomials don't have asymptotes, so I don't have to worry about that one. So Tierney, how about the first derivative then?
3x squared plus 12x plus 12.
Good. And then that sets us off on all the first derivative stuff. Increasing, decreasing intervals, which leads to maximums and minimums. Very nice that this one works out okay in terms of factoring. In fact, works out really nice. I only get one critical point. It's kind of a double root, so something's going on there. Let's see, a number line, but that means my interval is negative infinity to negative 2. Then negative 2 to infinity, and I've got 2 extra spots over there that I don't need. So I can test negative 3 and 0. And when I say test them, where am I testing them into? F or F prime? Or F double prime? F prime, because I want to learn where we're increasing and decreasing. So if I plug in negative 3, I get negative times a negative, which is a positive. And what's that mean? So what does that tell me? Good. F is increasing. I like that you said F is increasing. Don't just say increasing. Because if F prime is increasing, that's something else. F is increasing. I plug in 0, 3 times positive is a positive. So that means the same thing. F is increasing. So where is there a relative max? There's not one. And I don't know, it still says because. Why would you say there's not one? F prime doesn't change. I guess we could be real specific and say F prime does not change positive to negative. If you wanted to say because F is always increasing or because F prime is always positive, that would be a fine reason there too.
I was going to ask the double root thing, but that's a minimum, not a maximum. So I was going to be like, oh, is there not one of the balances?
So double root means it doesn't change signs there. And so the graph of f prime would have a bounce at -2. And that would mean, like if we graphed f prime, there's, whoops, at -2. So
but it's not F.
So there is a bounce, but the bounce is on f prime.
Okay,
And another way to say bounce is it doesn't change signs.
so it would be a point of inflection later, but no F.
So we do think, yeah, we're peeking ahead, but yeah, that's going to be a point of inflection
Hmm.
because f prime is changing, increasing to decreasing. That was weird. How about relative min? No, and same reason. Well, I guess not exactly the same reason. F prime. You know what? I'm going to say f prime is always positive. So I'll give a slightly different reason. If you just want to stick with f prime doesn't change negative to positive, that would be okay. So there's our, again, making sense of the bounce. There's a bounce, but the bounce is on f prime, not necessarily on f. So we're always increasing. So we didn't get any maxes or mins out of that. So that wasn't, I mean, it's helpful to know what the graph looks like. It wasn't helpful in terms of finding a point. Natalie, how about the second derivative?
6x plus 12.
6x plus 12. So now we're headed toward concavity stuff. Points of inflection. So again, -2. That's a result. Again, the double root stuff is like a whole separate issue, but if there's a double root in f prime, it's going to show up as a single root in f double prime. If there's a double root in f, there's going to be a single root there at f prime. That, I don't know, that takes care of itself though. So same intervals. Whoops, let's get that right, -2 to infinity. Same test points then, -3 and 0. But where am I testing these? Because f double prime, because I want to know something about concavity. So if I plug in -3, I get -18 plus 12 is negative. What does that tell me about f? Concave down. If I plug in 0, I get positive. That tells me that f is concave up. So do I have any points of inflection? Yes. At -2, comma. How do I figure out the y value? Plug it into f. So let's see, that would be -8 plus 24 minus 24 plus 7. Did I do that right? So that would be -1. So an inflection point at -2, -1. And maybe I label it. I don't have to label it, but when it comes to graphing it later, it might be helpful that it's marked as such. Okay, so we're increasing the whole way. We said we weren't concerned really about the limits for these because for polynomials, it's one's going to infinity, one's going to -infinity. We're not really worried about limits though. So I need to increase the whole way. I need to be concave down up to this point and then concave up after that. So concave down and then concave up. And hit the points that I already have. So it looks something like that. Questions, comments, concerns?